Okay, so in this example, what we're going to do is have a look at how you solve a typical MOSFET problem. So let's get straight into it. So we're told that considering ID sat, that's the saturation current. So the first thing just to note here, whoops, is what it's actually talking about. So just to recap, that for a MOSFET, you have something that looks like this. If this is the drain current, and remember that for a MOSFET it's nice and easy because the drain and the source current flowing through here and flowing through here are identical. Another point to note is that this point where the arrow is pointing out is the source. That's the drain. And the reason why that's the source, even though it's actually pointing in this direction, is because this is the direction of conventional current. So conventional current is actually flowing this way, which means that the electrons are actually flowing that way. Okay, so if they're flowing that way, going up like this, then this is actually the source of the electrons, like that. And that's the drain, because they're being drained away over here. So the conventional current is flowing this way. And that's why this is the source and this is the drain. And this is nice and easy, that's just the gate. And the other important principle to remember with a MOSFET is that, again, nice and easy, the current going into the gate is 0. There is no current that actually flows between the gate and the source and drain. All the drain current goes straight into the source, like this, okay? And what we can say is that if this is the VDS, the voltage drain source, then what we can say is that once the drain source voltage is enough, or it gets to a certain point, i.e. this point over here, it's not actually going to affect the current flowing through. And for all questions, we assume that we're going to be dealing with this region over here in saturation. So you don't really need to worry about what's going on kind of over here. And the condition for this is that the voltage, the drain source voltage, equals the overdrive voltage. Once the drain source voltage is greater than the overdrive voltage, then we can assume that we're in the saturation region. So often a condition that we can say is that VDS is greater than or equal to VOV, the overdrive voltage, and that being the voltage gate source minus the voltage threshold, of course, okay? So the only thing that really determines where this kind of level is, if it's kind of over here, like that, or like that, or like that, or like that, is actually determined by one parameter, and that's the gate source voltage. So once we are in this region over here, we can adjust the current flowing through, like that, simply by adjusting the gate source voltage between here and here, okay? And what we can see is that if we just note down the standard equation for the saturation current, okay, so we can call this ID sat, and that basically just describes the current in the saturation region like this, all of these different currents over here, okay? And it's only going to be a function of one variable, really, which is the gate source voltage, which we adjust. Remember, the threshold voltage is going to be constant. The materials are going to be constant. The width and the length of the channel are going to be constant. So it's really just going to be determined by this equation here, which is always going to be half Kn VOV squared. And that's it. That's the only thing really to remember for this. And Kn is the MOSFET transconductance parameter. which is simply going to be mu times Cox W on L. Okay, and this part over here is is sometimes referred to as Kn prime, and that is the another type of parameter that really just relates to the material, whereas if you combine that with the channel aspect ratio, you get Kn, the actual transconductance parameter. So sometimes you might need to work out what K of n actually is based on these things. And the overdrive voltage is just the voltage of the gate source minus the voltage of the threshold voltage. Because remember, if the gate source voltage is not greater than the threshold voltage, then there's no channel inversion that occurs, and no electrons can actually flow between the source and the drain. So beyond this point, it actually creates the channel. So that's the condition, and this is the equation that we can see over here. Now, if we just expand this equation, what we can see is that ID sat is going to equal to half Kn VOV, which is V gate source minus V threshold squared. And if we only adjust VGS, what we'll notice is that we should end up with some kind of relationship like this. Okay, and what this is, and again, if this is VDS and this is ID, we can see that as we adjust VGS, the gate source voltage, the saturation current is going to increase like this exponentially. And that's exactly why we end up with the kind of this thing that kind of, whoops, that was not very good, which kind of looks like this kind of curve. If you see any diagrams, that is basically the saturation current as a function of increasing gate source voltage. Okay, now let's proceed to answer the question. So now we start to see how the drain and source current, remember they're always the same, operate in the saturation region. And we can generally assume, and the question usually will say this, we can generally assume that we are operating in the saturation region, i.e. where the drain source voltage is greater than the overdrive voltage. So let's go into the question. So the question says, considering ID sat, so it's a saturation current, so that's already giving it away, really, that we're operating in this region here, is half mu Cox W on L, and remember mu Cox W on L is simply Kn, the transconductance parameter, times the overdrive voltage squared, so that's exactly what we have over here, where mu Cox W on L is 0.002 amps per volt squared. So again, this is Kn that we're given, and the threshold voltage is 1.75 volts. Assuming I bias is 1.65 milliamps, and estimate the small signal gain V out on Vn of the circuit at 100 kilohertz. So there's quite a lot of information there. Let's try and break this down. So the first thing is, when you're getting, I think, into a MOSFET question, is just recognize the IDIS, okay, which is corresponding to this part over here, okay, in the saturation region described by this equation over here. This is really like the golden equation for MOSFET analysis. Yeah. Now, we're given the equation for ID sat, which we really know already. We're also given Kn, this parameter, and we're also given the threshold voltage as well. Okay, so let's proceed to answer the question here. So we're told that ID sat equals half mu Cox W on L VGS minus V threshold squared. Okay, so that's basically just reiterating that the ID sat is always going to equal half Kn VOV squared. It's in the simplest notation. Okay, and we're told Kn, the MOSFET transconductance parameter, is mu Cox W1L, 0.02 amps per volt squared. So that's going to equal half of 0.002 times VOV, the overdrive voltage, which is the voltage gate source, minus the threshold voltage, which we're told is 1.75 volts squared. Okay. And the other thing that we're told, if you look very carefully, is that we're actually given the ID sat, the saturation current, over here. So you can see here the I bias. This is the current flowing from the source over here. And we're told the I bias is 1.65 milliamps. So we can actually say that 1.65 times 10 to the minus 3 equals half of this, which is 0.001 times VGS minus 1.75 squared. Okay, so I'm going to take this to the other side, divided by 0.001. Now, what we can't do is simply square root that and square root that and then say VGS equals this. Can't do that. And the reason that we can't do that is because we need to find VG over here and VS over here, because VGS over here really means, if we just do this in a different color, we can say that VGS actually means the gate voltage minus the source voltage over here. Okay, so let's calculate what the gate voltage is over here first of all. And the important thing to remember over here when we're working out the bias voltages at DC is that we take all the capacitance. So if we know that the capacitance of a capacitor, sorry, the impedance of a capacitor is 1 over J omega C. And at DC, this becomes 0, so this becomes 0, so this becomes infinite. In other words, we block all, we effectively open circuit this. So we'll just cross this out over here. We'll cross the capacitor out over here, we'll cross the capacitor out over here, and everything else kind of disappears because it does not really connect to the circuit. We also short circuit any DC voltages, and we open circuit any DC current sources as well. So we're actually going to open circuit that thing over there. And what we want to do is find the gate voltage over here, okay? So that we can insert that over here. And then we're going to replace that into this equation over here. And then we'll be able to find the source voltage, which will be the voltage over here, okay? So let's go ahead and do that now. So using the principle of superposition, we can say the following. We can say 24 times 1 over 6 minus 24 times 5 on 6, and that should give you the voltage in the middle section over here, okay? Okay. And that equals minus 16. Okay, minus 16 volts. And that is the that's the voltage over here, just at that point, the gate voltage. So we can say VG equals minus 16 volts. Okay. Now what we can do is substitute this back into here and back into here and actually solve the equation for Vs. And that implies that Vs is going to equal minus 19.03 volts. And we can therefore say that VGS is VG minus Vs, which equals minus 16 minus minus, which is plus 19.03. And that gives us 3.03 volts for the gate source voltage. We also know that GM equals KN VOV, and this is going to be important because we're going to need to work out what the reciprocal is, 1 over GM, and that's going to form part of the resistance in the hybrid pi model, which we're asked to do, estimate the small signal gain of the circuit, the small signal gain. So we're going to need to look at the hybrid pi model for this, or the hybrid T. Let's have a look at this. So GM equals KN VOV, and we know that KN is 0.002, and VOV is the overdrive voltage, which is the voltage gate source minus voltage threshold, which equals 0.002, and the gate source voltage we now know is 3.03 volts, and that was why it was really important to work out what the gate voltage was over here, and the source voltage over here. And remember, the gate voltage was worked out from the biasing at DC level, okay. And the source, or the drain source current, and the voltage from that was worked out via the standard equation of ID sat equals half Kn VOV squared. So we basically had every single parameter for this, apart from Vs. Okay, so again, we worked out Vg from DC biasing over here. We worked out Vs by solving this equation over here. And that equals 0.002. The gate source voltage is 3.03 minus the threshold voltage, which we're told is 1.75. So if we do that, 3.03 minus 1.75 times 0.002, and that gives us 2.56 times 10 to the minus 3. And therefore we can say that 1 over GM, which is really the resistance that we're going to need, is going to be 390 ohms. And that's going to be really important when we do the small signal model. Okay, so the next step is we're going to use a hybrid T model of the MOSFET. There is a hybrid pi model, and you choose one or the other based on what analysis you're going to do. It really takes a lot of experience to know which one you're going to use. For our circuit here, this is actually going to work. But I don't think there's really a rule to know which model to use. It's more like a trial and error, and just from experience you'll know which one to use. It depends on whether or not you'll need a resistor in this path or not. So let's consider taking the circuit that we have over here and implementing it into the hybrid pi model over here. Let's do that. So let's take the source first. So the source over here is going to be everything happening over here. And what we have to remember now is that we're going to be analyzing the circuit at 100 kilohertz. So we're not looking at DC biasing anymore. So what we can say is that we can actually start to include these capacitors, because these capacitors are going to act as short circuit at AC. And just to go over the reason for that, so if we say the impedance of a capacitor is 1 over j omega c, if the frequency is very, very high, then we can say that this is going to be very low, i.e. tending towards a short circuit. Okay? So you can actually assume that those are actually going to be short circuits. And another thing at high frequency as well is that these current sources will be effectively open circuit, or they'll go to ground. Okay, so what we have is at the source over here, we're going to have this path going like that. Yeah, because current sources are open, I believe. So the path is going to be going like this from the source. So we've got the source over here, and we're going to encounter a 50 ohm resistor. So we'll place that in over there, and then we're going to have Vn, and that's going to go to ground. Sorry, it's a bit small. And then at the drain side, so let's have a look at the drain. The drain is going to be over here, and we can see that, again, remember at high frequency, this is going to be grounded, and this is going to be shorted. So we're going to have this resistor in parallel with this resistor, okay, for the drain. So we can just put a resistor in there of 10 kilo ohms and 20 kilo ohms in parallel, and that's going to be 6666 .6 recurring ohms, and that's going to go to ground. And then we're going to have the voltage being measured over here, V out over there. And now let's consider the gate. So the gate will be connected to this thing, and the gate will be over here. And remember, we're AC now, fairly high frequency, 100 kilohertz. So what we're going to have is that, again, this is going to be grounded, this is going to be grounded, so we've got two resistors here and here in parallel connected to ground. And those two, if we do that, 5 times 10 to the 6 times 1 times 10 to the 6 divided by 6 times 10 to the 6. I'm just going to do that again to make sure. 5 times 10 to the 6 times 1 times 10 to the 6 divided by 6 times 10 to the 6. Yeah. Okay, so that's going to be 833 kilo ohms for that resistor over there, and then this is kind of going to ground as well. So the question that we have to ask ourselves now is, oh sorry, forgot to put that resistor in there, 390 ohms as well. So we'll just pop that in, and we'll say 390 ohms, okay? And that's going to be the resistance of the source resistor over here. So what we have to ask ourselves now is, how are we going to find the V out on V in? We've got V in over here, and we've got V out over here. And we need to find a way of finding V out on V in. That's the purpose of the whole task, which is the gain, small signal gain. So how can we do that? Well, it's usually easier to start from the output voltage and deal with that first. So we can immediately say that V out, V equals IR, and the current over here is actually flowing away from the ground, which is opposite to where it normally goes. And we know that because of the direction of the arrow of the current over here. So it's actually flowing like that. Normally, current will flow towards the ground. The fact that it's flowing away from the ground means that it's negative. So it's going to be minus ID times the resistance over here, which is going to be 6666.6 recurring. So we've managed to find the output voltage, and obviously when we're dealing with MOSFETs, the nice thing about MOSFETs is that the drain source and the drain current and the source current are identical, and that's going to be really important. So the next thing is to try and figure out what the input voltage is in terms of the ID or IS, and that way we'll be able to say V out on V in, and they'll hopefully have some cancellation, and we'll be able to work out what's going on. So if we examine this path over here, what we can see is we could either apply Kirchhoff's law, Kirchhoff's current law, and we could say that we've got a voltage here, V in, between here and here, and we've got two resistances over here, between here and here. Okay? So we've got one voltage and we've got two resistors. So we can maybe find an expression for the current. So we could say and we've also got to take into account the direction as well of the current. So if we look at the source over here, remember the current is moving away from the source, and it's going to ground like this. So the current is actually flowing this way, but the voltage is actually this way. So there's going to be a negative relationship between the voltage and the current over here as well. So we could say, again, V equals IR. So we could say that V in equals IS times the resistance on that path, which is 390 plus 50, which is 440. And now we have a relationship between V in, oh, that should be negative, of course, as well. Now, we can also say that IS equals ID. So we can say that V in equals minus ID times 440. And therefore we can say, let's go back to, let's do darker green. Therefore we can say that V out on V in equals minus ID, 6666.6 recurring, on minus ID 440. And that equals 15.15. And that is the small signal gain at high frequency.